Hello students, let's begin with our second session on nuclear chemistry, and today we are going to cover various radioactive disintegration series, nuclear fusion and fission, chain reaction, spallation and projectile capture reaction, nuclear energy and various applications of radioactivity. Let's begin with the radioactive disintegration series. A series of spontaneous radioactive decay that takes place in a radioactive element and continues on its own, giving rise to a new end product, is known as a radioactive disintegration series. There can be a number of intermediate products involved which are also radioactive. 4 such series are known to us. They are Thorium Series, Neptunian Series, Uranium Series and Actinium Series. Out of which Neptunian Series is the only artificial series. The rest 3, that are the Thorium Series, the Uranium Series and Actinium Series, are natural. This table gives us some basic information about all the 4 series. The first series is the Thorium Series, in which the starting isotope is thorium-232 and the end product is lead-208. 6 alpha particles and 4 beta particles are emitted in this conversion. This series is also known as 4n series because the mass number of every isotope of this series can be represented as 4n, where n is an integer. The next series is the Neptunium series. Its starting isotope is Neptunium-241 and the final product is Thorium-205. Due to the short life of its starting isotope, this series is already extinct on Earth. Some of the older sources say that the final product is Bismuth-209, but it has been found that it is also radioactive and its half-life is of the order of 10 raised to 19 years, and it ultimately gets converted into Thallium-205. This last step is the only rate-limiting step which still exists. 9 alpha particles and 5 beta particles are emitted in this conversion. This series is also known as 4n plus 1 series, since the mass number of every isotope of this series can be represented as 4n plus 1, where n is an integer. The third series, Uranium Series, is also a natural series like the Thorium Series. Its starting isotope is Uranium-238 and final product is lead-206. 8 alpha particles and 6 beta particles are emitted in this conversion, and it is also known as 4n plus 2 series. The last series, the Actinium Series, is also a natural series with Uranium-235 as the starting isotope and lead-207 as the final product. 7 alpha particles and 4 beta particles are emitted in this conversion, and the mass number of every isotope of this series can be represented by 4n plus 3. This is a diagrammatic representation of the Thorium series, that is the first 4n series we were talking about. The starting isotope, as you can see, is Thorium-232. It emits an alpha particle and gets converted into Radium-228, which then emits a beta particle to form Actinium-228. It emits a beta particle and forms Thorium-228, which gets converted into Radium-224 by emitting an alpha particle. It again emits an alpha particle and forms Radon-220, which again emits an alpha particle to form Polonium-216. An alpha particle is again emitted, forming Lead-212, which emits a beta particle to form Bismuth-212. Now, most of the part of Bismuth-212 gets converted into Polonium-212 by emitting a beta particle, which then emits an alpha particle and forms Lead-208, which is the final product. But some amount of Bismuth-212, that is nearly 35.9%, forms Thallium-208 by emitting an alpha particle, which then emits a beta particle to get converted into the final product. This is a diagrammatic representation of the Uranium series. The starting isotope, as we discussed, is Uranium-238 and the final product is Lead-206. These blue arrows show the path which is followed by most of the atoms, and a very small percentage of the atoms follow the alternate routes that are shown by white arrows. We'll discuss the main route, which is followed by more than 99% of the atoms. Uranium-238 emits an alpha particle and forms thorium-234, which emits a beta particle and forms protactinium-234. Again, a beta particle is emitted and uranium-234 is formed, which emits an alpha particle to form thorium-230. It emits an alpha particle to form radium-226, which again emits an alpha particle, converting into radon-222. It emits an alpha particle to form polonium-218, which then again emits an alpha particle to form lead-214. A beta particle is emitted and it gets converted into bismuth-214, which then forms polonium-214 by emitting a beta particle. It emits an alpha particle to form lead-210, which then again emits a beta particle to form bismuth-210. It emits a beta particle forming polonium and then again an alpha particle forming lead-206. The last natural series is the Actinium Series. Uranium-235 is the starting isotope. It emits an alpha particle forming thorium-231, which emits a beta particle getting converted into protactinium-231. It again emits an alpha particle forming actinium-227, which then either forms thorium-227 or a small amount of it may form francium-223. Let's consider this route since major percentage, that is more than 98%, forms thorium-227. It then emits an alpha particle forming radium-223, which then again forms radon-219 by emitting an alpha particle. It again releases an alpha particle forming polonium-215, which releases an alpha particle forming lead-211. It emits a beta particle forming bismuth-211, which then emits an alpha particle forming thallium-207, which then gets converted into the final product, that is lead-207, by emitting a beta particle. Nuclear reactions. A nuclear reaction can be defined as a process in which two or more nuclei or nuclear particles collide with each other to form products which are different from the reactants. There is a difference between a nuclear reaction and a radioactive decay. Radioactive decay is spontaneous and is not affected by the experimental conditions, so it is an inherent property of that radioactive isotope or element. Whereas a nuclear reaction has to be initiated by a particle and may require certain conditions to take place. The process in which two or more nuclei or particles collide and separate from each other without undergoing any change at all is known as elastic collision. On the basis of the target nucleus which participates in the nuclear reaction and the products that are formed, we can differentiate nuclear reactions into two types. The first are the fission reactions and the second are the fusion reactions. Fission reaction. It was first observed by two scientists, Otto Hahn and Stresemann, in 1939. We can define nuclear fission, which is also known as spontaneous fission, as the nuclear reaction in which a heavy nucleus splits into two or more parts, usually by absorbing a particle or radiation. Let's take an example. One neutron collides with uranium-235 nucleus and splits it into two lighter nuclei, barium-141 and krypton-92, along with emission of three more neutrons. A great amount of energy is also released in this reaction. Now, for that energy to be useful, the energy should not be released over a long period of time. For example, uranium-238 spontaneously disintegrates into barium and krypton, producing large amount of energy. But since the half-life of uranium-238 is around 1016 years, the energy is released over such a long span of time that it is hardly of any use to us. Now, one way to overcome this problem is to induce fission, that is, to bombard a heavy nuclei with particles such that the nuclei splits into lighter fragments. We can visualize the fission reaction like this. This is a heavy nucleus, uranium-235 in our example, and this is a neutron which is going to collide with the uranium nucleus, causing it to split into lighter nuclei, which are barium-141 and krypton-92 in this example. This splitting is accompanied by emission of some other particles, which are 3 neutrons in this case.